Welcome to this presentation on wireless modules versus SoCs, trade-offs and decision-making criteria. My name is Nick Dutton, I'm with Silicon Labs. Let's get started. Deciding between an SoC and a module might appear to be a straightforward decision, but the hidden costs can often account for a product being the profitable success that a company hopes it to be, or the reason for a product's success being hampered. In this presentation, I hope to illustrate how modules may actually be your lower cost solution. Today's semiconductor products are highly integrated devices, complete with all of the analog, digital, radio, and microcontroller capability that truly make them a system on chip, or SoC. An SoC will always be the lowest bill of materials, or BOM for short, but it is always going to be more complex to design with. To implement a design with an SoC, a developer will ideally need to be looking at a high volume product and will be supported by a sizable R&D budget, along with all the tools he needs to perform antenna measurements. They will also need the time in which to perform the necessary prototyping rounds. They will need to dial in the RF design to meet the compliance testing and filing process. Developers that use modules will have all the features of the SoC, but they will also have a solution that adds the external components, maybe the antenna and an RF shield. Due to this additional integration, modules are often pre-certified for RF compliance, and this is done with the various regulatory authorities around the world. As modules are more of a solution than a component, they will always cost more than the SoC itself. But as this presentation will illustrate, they will typically become more convenient and prove better value for money with a greater return on investment in most use cases. So when does a module appear to make sense? Most developers that use modules will quickly understand they're on a path with a solution that gets them to market quickly with reduced risk, a development path that doesn't need expensive RF expertise on staff, and an ability to design without expensive lab time or specialist RF design equipment. Developers also find that their limited engineering resource isn't tied up on a single project for longer than absolutely necessary through multiple design iterations. Also, surprisingly for many, modules can offer developers a much smaller PCB footprint than SoCs, and this is because of today's System in Package or SiP technology. SiP technology allows for ultra-dense packaging using three-dimensional stacking of components inside the module. This is a process not typically done on a traditional PCB design. The SiP module, as can be seen here in the bottom of the screen and second from the right, provides a solution that is fully certified, simple to design with, and offers the smallest overall physical footprint. As we've discussed, however, SoCs provide the lowest cost bill of materials, particularly, as with the case of Silicon Labs, the SoCs are designed to reduce the number of external components. Here we see the bill of materials illustration of the Silicon Labs EFR32 BG22 SoC, which is also documented in the application note 933.2. This application note is available directly from the Silicon Labs website. The application note discusses a real design based on the BG22 and proves good RF performance. The bill of material shows a 38.4 MHz crystal which doesn't need external loading capacitors because it's tuned internally. The design uses a 3-element matching circuit for the antenna to filter the harmonics, a DC blocking capacitor, and an LC tank circuit for the DC-DC converter. The DC-DC converter is built into the SoC and can also offer additional power rails to power digital IOs on the RF supply along with any external components. A solution would also need the standard decoupling capacitors, an antenna, and a shield. Depending on the exact implementation, the external components could amount to between 30 and 80 cents in addition to the cost of the actual SoC. This design uses an internal precision RC oscillator so an external low-frequency crystal can be eliminated. The oscillator is accurate to 500 parts per million, or ppm, which is an intentional design feature as that ensures it meets the BLE timing requirements. The SoC also offers an incredibly accurate temperature sensor, a typical feature of any SoC, but this one supersedes the typical plus or minus 5 degree accuracy with an accuracy of plus or minus 1.5 degrees. In general though, not all SoCs are created equally. Not all vendors will offer balance or enough flash for firmware updates of the stacks or applications. They may require an external crystal or a more complex antenna match, so the overall bill of materials might actually be a lot higher. So as expected, the first recommendation is to do a break-even analysis. This is the first place a developer should go to understand the costs involved. This illustration is designed to show net profit of given implementations using the SoC and the module approach. The module, shown in yellow, already has the cost of the module development and certification built in. Therefore, its accountability is very simple. The SoC implementation shown in blue, however, needs this cost adding to the SoC, and therefore, as you would expect, due to the negative upfront costs and lower volumes, profit initially will show as a negative. As these costs are divided over the volumes and the volume pricing is applied, profit will increase and at some point provide a greater profit than that of the module implementation. In this case, the point at which they cross is about 300,000, a number which often surprises many. The crossover point for SoCs and modules has also moved higher and higher over the years, and with some examples even as high as 1 million pieces. Furthermore, even though the price of SoCs has gotten lower over the years, so has the delta between SoCs and modules. A break-even analysis isn't the only thing to consider. An SoC implementation requires much more design effort. With more design effort, there is also greater risk of surprises and delays. So, how do delays affect the business plan? Is the plan based on a guarantee of revenue by a certain point? How will it impact the business? How might it affect cash flow? And if we're willing to accept a suboptimal RF design for our product, will the customer accept it? We all know how negative customer reviews can kill a product early in the market. A key source of these problems often comes during compliance testing. This is where many of the surprises, design changes, and delays can occur. Now, modules have the advantage that they reduce this design risk and can therefore shorten the time to market. Even some of the world's largest companies opt to use modules over accepting the risk to their business plans. By example, if we look inside this smartphone design, which sells in volumes of about 200 million pieces per year, we can still see several modules. The one that I've got highlighted is actually a Wi-Fi Bluetooth module. In such volumes, the vendor could easily justify a chip-down design. They have access to all the RF engineering and equipment they could possibly need. But for risk mitigation, they still choose modules. It's important, therefore, to not only perform the cost comparison, but a break-even analysis and a review of the business plan to account for the risk and delay. So let's look at some of the several hidden costs. The first being in RF engineering. RF engineers are an expensive commodity. The Glassdoor website suggests a loaded salary is anywhere between 100 and 200k per year. Even if a company has an RF engineer on staff, there are only so many projects that he or she can do in any given year. RF engineering is complex because no one project is the same. Each will have its own design challenges, influenced by the product housing, antenna types, and peripheral circuitry. The parasitics change from board to board and project to project. RF engineers ensure the impact of these variables are minimized. When using a module, much of this complex design work has already been completed by an RF expert. The second hidden cost is the cost of RF lab equipment. The illustration shown here shows the typical list that an RF engineer is likely to need. While it includes spectrum analyzers and antenna positioning gimbals, it may also include access to special RF labs called anechoic chambers, which are designed to provide accurate readings by stopping both RF reflections, echoes, and environmental RF noise from affecting the measurements. It may not be necessary to buy all test equipment because often companies will have access to equipment rental companies. But even this option can be expensive, as renting equipment can cost a few $1,000s per day. PCB layout and antenna matching is a deceptively hidden cost. How difficult can it really be? Well, every RF design has parasitics, and every component in the design, even the PCB traces, must be considered. Most RF engineers will tell you that antenna tuning is an iterative, time-consuming process, requiring multiple board spins and even with the end product plastics in place. For developers implementing their own SoC designs, Silicon Labs offers a number of documents aimed at helping them with these antenna match issues and PCB layout guidelines. Once a developer thinks that they've got their product ready, regulatory approvals come in. And regulatory approvals vary from country to country, with each territory maintaining a formal agency designed to regulate how products share their airwaves. For example, in the US, there is the Federal Communications Commission, or FCC. In Canada, it's the Agency for Innovation, Science and Economic Development. Europe has the European Telecommunications Standards Institute, or ETSI. Approvals can be costly because every product needs to be tested for every location that the developer intends to sell it in. Unfortunately, regulations also do tend to change, and the developer needs to stay appraised of these regulations. The use of modules does help minimize this overhead, as the module vendors will manage this for you. Most certification bodies also recognize the modular approach, and end products will inherit those modular certifications. In addition to regulatory certification, there are also often industry alliance certifications which govern the protocol. Industry alliance certifications can vary depending on the associated alliance. By example, if you use a Bluetooth module, it tends to only be a paperwork exercise. But other solutions, such as Wi-Fi, Zigbee, or Z-Wave, require mandatory end product compliance testing. In all cases, however, Silicon Labs tests its stacks and its hardware solutions ahead of time to ensure there won't be any issues when a developer does their own alliance testing. Finally, we shouldn't forget that products will also likely require UL safety testing, or FCC Part 15B, which will be required even if there is no wireless aspects to a design. Everything we've covered so far tends to be about the physical product. There is another aspect that should be taken into account, and this is the cost of missed opportunity. It's a difficult aspect to quantify, but it can be illustrated. In this diagram, we can see that the path of a typical product will follow from RF design through to a fully certified product. This journey is the same for all designs, but the time taken by each step is different for modules and SoCs. Also, a number of the steps may be repeated as parts of the design fail. When averaging the time customers take to implement a design, we tend to see a common trend, and using those numbers, we can make certain approximations as to the cost a delay will create. On average, an SoC developer will take between 6 and 16 weeks to create a design. By contrast, a module-based design typically takes between 2 and 4 weeks. While these numbers may change from technology to technology, the relationship tends to remain constant. So what does the design delay cost? In the tables below, we make a number of assumptions, and you should certainly apply your own numbers when trying to quantify this cost. But here we look at a few volume breaks, and we assume that the revenue we would expect to see is loosely connected to some formula from which the cost of goods came. Since we are looking at the costs of delay and associating that with RF design, we will use that only as part of our benchmark. So for example, if we wanted to add wireless to a product, and if we use a number, say $4 for the cost of a module, and apply our formula to work out the end customer price, maybe we can assume this equates to $83,000 in extra revenue for that year. As we apply volume discounts to both the cost of goods and the retail price point, maybe that creates $5.2 million at 1 million pieces. This gives us a baseline from which we can now take a look at our design approach. If we now change from a module to an SoC in these volumes, and we put aside the additional design and certification costs for a moment, we could now see what we could save. So at 1 million pieces, that might equate to $1.25 million. But remember, it might take us 12 more weeks to release that product. 12 weeks is a quarter of that $5.2 million that we were going to make if we used the module. 12 weeks is therefore about 1.3 million of that 5.2. So again, without accounting for the additional costs or tying up of our engineers for an extra 12 weeks, that delay effectively incurred by an SoC design cost us what we would have made by getting to the market on time. While I know this is a coarse illustration, it does show us that the lower COGS of an SoC could in fact create a false economy which costs us more in the long run. We shouldn't forget also that the supply chain and associated quality assurance becomes more expensive the more complex our design becomes. As an SoC-based design could have easily 15 more components, that all needs to be managed. This means additional forecasting and additional inventory management cost. The inventory may also be supplied by multiple vendors, each with their own stock levels, minimum order quantities, distribution chains, and lead times. Furthermore, for quality assurance, there are additional costs incurred by incoming inspections and failure analysis protocols when they're needed. With more components, there is also an increased likelihood of manufacturing issues, such as cold solder joints or pick-and-place machine errors. When using a module, these variables are reduced. When using a module, the variable numbers are reduced. There is one component to manage and a single vendor to coordinate and work with. So in review, there are clearly good reasons behind a chip-down design based on an SoC. It certainly offers the lowest bill of materials in high volume, and a cost analysis will allow you to find your break-even point. An SoC design will require greater levels of RF expertise, a specialist lab, equipment, and software. Your business plan will need to accommodate longer development schedules, and will need to include multiple design iterations followed by several certification processes. The Silicon Labs portfolio is designed to support chip-down SoC developers with plenty of documentation such as application notes specifically designed to address antenna match, or offer full reference designs complete with source files. The portfolio also offers modules for developers looking for the lower risk and faster time to market. The pictures in this illustration show the radio boards we use in our evaluation and development kits. The top picture shows a full SoC option along with all the additional discrete components. The other shows the SIP module option. It's also very clear from a visual understanding of why the module is very simple to implement. As the software is the same for both the SoC and the SIP, developers can start by using the SIP as a stepping stone to an SoC design once their volumes start coming in. So to summarize, this module-based stepping stone is useful because it ensures revenue is not lost while a lower cost bill of materials version based on the SoC is in design. And you still get the benefit of lower risk and better time to market, but now you also get the longer term lower cost bill of materials through chip-down design. To close our presentation, I wanted to briefly show you this slide. These are the modules to support all of our main SoC devices. Whether you are looking for a traditional PCB design, or for very specific market optimized versions such as the MGM210L, which is designed specifically to fit inside a light bulb. It also shows the small 6x6 SIP variant that we've been talking about in the previous slide. So whether you are convinced you want an SoC design or whether you're convinced you want to go with a module design, we have a broad portfolio to help you no matter your selected architecture. We look forward to talking to you in a further presentation. Thanks again.